Morning, everyone. Hope you guys are doing okay. We are going to lecture on chapter 2. Just a second, pull that up. So chapter 1, we only did a little bit off of that. You'll definitely want to go back and do the assignments, the assignment for chapter 1, and just read over any missed information. And then today I will be posting these videos along with my other classes all on Thursday. I'll post these on the YouTube channel, organizing them by playlist. So if you want, you can rewatch certain sections, or if you missed a lecture, you can rewatch a lecture or watch it for the first time. Okay. So chemistry and measurements is the second chapter. This chapter is a lot of converting between units. So when we measure something, say we measure somebody's height, we need to apply a unit to it to give it meaning. It's not enough to just say, oh, you know, like this person here, for instance, oh, they're 1.65. You may be thinking, oh, are they like 1.65 feet? Because that means they're really teeny tiny. We have to give a unit. So in this case, it's 1.65 meters, which is equivalent to roughly 65 inches. Same thing with her weight, right? 58.2. What are we saying? She's 58.2 pounds. That would be quite tiny for a college student. No, she's 58.2 kilograms. She's 128 pounds. So this second part here is just as important as the number itself. So you want to get in the habit of not just writing numbers, but also giving a unit. One second. Sorry, trying to pull up my additional notes so that I don't forget anything. All right. So as far as units are concerned, you may be more comfortable with the ones that are in parentheses, the inches, the pounds, the miles. Those are the British system. We are going to steer away from those for this class and move towards the metric system, which are the first units that we see: meters, grams, kilograms, kilometers, things like that. So scientists use the metric system, and then pretty much every country outside of the United States, and even Great Britain, they use the British system, but they also use the metric system a lot. use this metric system. And part of it is adopted and slightly modified to come up with this thing called the International System of Units, or the SI units, which is the official system for measuring length, volume, mass, temperature in all the sciences throughout the world. So, we don't have scientists in the States saying, oh, it's 15 pounds, and then in somebody in Africa reporting it in kilograms. Everybody is going to honor kilograms if they're in the scientific field. So here are the units. This is the metric, and then this is the SI. They're pretty close to each other. It's a couple changes. So length, both of those are in meters. Volume, the metric system is in liters. The SI unit is the cubic meter. Now, think about volume. Volume is something that occupies space. So we have like a length times a width times a height. That's why we have that cubed value. Mass, the metric is grams. The SI is actually the kilogram. The gram is such a small value, we tend to use kilogram for SI. Temperature, the metric is Celsius. The SI is Kelvin, and those two relate to each other pretty easily with just an addition or a subtraction of 273, and we'll go over that. Time is second, all over the board. So here is length. We've got a meter stick on top here. On the bottom, we have a yardstick. A yardstick is 3 feet. A meter stick is going to be slightly longer than that. We can see that if we take our meter stick and we cut it into smaller parts, we get these little tick marks. We have them the bigger numbers are at the decimeter. The smaller ticks are at the centimeter. Now, the convenient thing between these two is that there are 100 centimeters in every 1 meter. So it's all based on a scale of 10, right? As we want to increase units, we multiply by some sort of factor of 10. We want to decrease units, we divide by a factor of 10. That isn't the case for the British system. We have a yardstick here, 3 feet. Each foot is 12 inches. We can see here, these are 12 of these, and then within each inch, right, we cut that up into eighths, or in this case, they have it in fourths, but sometimes they'll narrow it down even farther to eighths. So it's just really messy because none of the numbers are congruent with each other. If we look at volume, so this is known as a graduated cylinder. It has a series of numbers up along the side, and you can really quickly and pretty accurately get a volume measurement for a certain amount of liquid. 1 liter is equal to 1,000 milliliters. The little m in the front here is not talking about meter, it's talking about milli, and we'll talk about prefixes in a little bit. Here are some other things known as conversion factors or equivalencies. So 1 liter is roughly equal to 1.06 quarts. It means that we've got 2 different units. They're talking about the same amount though. We're just shifting them into different units. We've got mass in grams and kilograms. So 1 kilogram has 1,000 grams to it. Hold on 1 second. Gabby, go bother Daddy. Sorry. Darn. I still don't know where my husband is. He's supposed to watch the kids for an hour and 15 minutes every day so I can lecture, and he just disappears on me. All right. So here's a relationship between a British and a metric system. If you're on Earth, this applies. 1 pound is equal to roughly 454 grams. That value. Hold on. That's my French bulldog. He's freaking out. We need to bring him out of here. Turkey. Turkey, come here, bud. You can say hi real quick. Say hi. Okay. You're crazy though, so you need to go out. Go. Okay, we can do this. So if you were to figure out this relationship would shift if we were like, let's say we were on the moon or something, because your pound value would change. Your mass value wouldn't change unless you stopped eating, but the pound value would shift. He is adorable. I think he's the cutest man in the world outside of my husband. He's just the cutest little thing. All right, temperature. So Celsius and Kelvin. This one's always hard to kind of wrap your head around because we're so used to Fahrenheit. Fahrenheit, water freezes at 32 degrees Fahrenheit. And this should be Celsius. I don't know why they have this as Fahrenheit. Water freezes at 0 degrees Celsius. Celsius is just a little bit more conducive for measuring experimental values, because water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. The numbers just work a lot nicer than 32 degrees Celsius or Fahrenheit, and like 212 Fahrenheit is what water boils at. I don't like that number. Time, seconds. Okay, that's easy peasy. So, all right, so when we're measuring a number, let's say we're measuring the length of this stick here. We can measure it, but we're only as good as like our piece of equipment that we're using as a measurement. So if we have a pretty crappy ruler, the length isn't going to be very precise. The last digit within our measured value is always going to be an estimated digit. So when looking at this thing here, I would say that this is, 1, 2, 3, 4 centimeters. And then I'd estimate a half, right? It's about 4.5 centimeters. It's definitely not on 4. It's definitely not on 5. It's somewhere in between. So I'd say 4.5. That 0.5 value is an estimated value. You always can estimate one past whatever your tick mark values are. So measured numbers are numbers that are obtained when you get them experimentally, things like height, weight, temperature. To write a measured number, observe the numerical value of mark lines, estimate the value between mark lines, use the estimated number as the final number on your measured number. So looking at these situations here, this is the one that we already talked about, but I've got just the broader tick marks. So I'm going to count up my ticks, 1, 2, 3, 4, and then I'm going to estimate that I'm somewhere halfway between the 4 and the 5, or I'm going to go with 4.5. Now, when looking at this number here, this final number, this is your estimated number. Okay, the 4 we know for sure, the 0.5, we're, maybe you are looking at this and saying, oh, it's more like 0.6. I want to go with 0.6. Okay, that's fine. There's sort of room for interpretation in that last number. Now, what happens here when we have a ruler that is a little bit better? So not only do I have the bigger ticks, I've got smaller tick marks. So now I can actually push my precision out another decimal place. I know for sure that I've crossed the 4. Then I'm going to cut this centimeter into these little things here, which are known as millimeters, and count up how many I have of those. So 1, 2, 3, 4, 5. I definitely go past the 5. I haven't quite reached the 6. So I've got 4.5. I know for sure this 5 is happening. And then I have to guesstimate that I'm somewhere between the 0.5 and the 0.6. So that's where I go with that 4.55. And this one, this final number here is the estimated value. Do you see how this number here is more precise than this number here? This number we would say has 2 significant figures. This number here we would say has 3 significant figures. It's a little bit more precise than the previous one. What if we happen to get in a situation where we land right on the 3, like boom, I'm on that 3. Well, I still have to estimate one decimal place past whatever the ticks are. So I'm at 1, 2, 3. So I know the 3 for sure. And I'm saying, no, I'm not just on 3. I'm on like right on 3. So I'm going to say I'm 3.0. The 0 is, again, the estimated value. Okay. So sometimes you have to add a 0 if you need to increase your precision. We wouldn't want to just leave it as 3. So and this number here, I would say has 2 significant figures. So whenever we're looking at measured numbers, this isn't counted values, okay? So if I'm counting, like I have 6 eggs, that's a discrete counting number that has an infinite number of sig figs. I'm not gonna get better at counting 6 eggs if I have a more precise ruler. They're just 6 eggs. It's like the definition of what I have. But in measured values, the number of significant figures are all the digits, including the estimated digit, that tell us something about precision. There are a couple rules that you need to follow when calculating significant figures. Significant figures are used to represent the amount of error associated with a measurement. So if you have more significant figures, less error, less significant figures, more error. All non-zero digits and zeros between digits are significant. They're telling us something about precision. So I'm just going to hop over here real quick. Still have this lingering cough. Does not want to go away. Okay, so if I write a number like, no, I don't want to do that one. 385. This would have 3 sig figs. All non-zero values, always significant if they're written. If I was to write a number 40001, as far as the number of sig figs, the 4 is significant, the 1 is significant, and the zeros in between are also significant. So in this, we'd have 1, 2, 3, 4, 5. 5 significant figures, or 5 figures of precision. Your significance, like your precision, happens in a chunk, okay? So you can't have significance here and then all of a sudden lose your significance or your precision and then regain it over here. That is not how it goes. It's going to happen in a chunk, all right? All of the numbers within that sort of bracket will be significant. So that's why the zeros in between, we're gonna classify those as significant. Let's look at a couple of the other rules. The zeros are what are going to throw you off. Those are the tricky things. So not zeros that act as placeholders before a digit. Zeros at the end of a decimal number. All right, so let's look at some of these. So this sort of gives us an example of each as we go through. So a significant figure, if it's not 0. So this has 2, this has 5. 0 between non-zero digits. So 205, we would say 3 sig figs. How about this one here, 5.008? Well, we know the 5 is significant and we know the 8 is significant, so the zeros in between have to be significant. A 0 at the end of a decimaled number, we are going to say those are significant. So 50 with a decimal there, the 0 in front is significant. The decimal is indicating to the reader that you've measured out to that value. 25.0. This isn't just 1, 2, it's actually 3 sig figs. If this 0 wasn't significant, the scientist would have just left it off, right? Like, why did he go through and write that 0? He wrote it to tell you that his measurement of 25 degrees Celsius is precise to the 10th place. Same thing with this here. It isn't just 16 grams to the ones place. It's 16 grams and it's actually been measured out to the 100th place. So these 2 zeros after the decimal are significant. Otherwise, they would just not write those and they'd just write 16. If you are looking at a number in scientific notation, all of the values that are in the coefficient are significant. So 4.8, we would say 2 sig figs. 5.70, all three of those are significant. Again, the writer wouldn't add the 0 if it didn't indicate some sort of precision or significance. When are zeros not significant? So a 0 is not significant if it's at the beginning of a decimal number. So you want to find your root number. Here's the 0.075. The number really starts with the 7. This 0 in the front, and same thing with this 0.0004, these zeros in the front are not giving us anything about precision. They're just telling us how small the number is. They're acting as a placeholder. So I don't include those as being significant. We add significance or we add precision on the tail end or the right side, not up in the front on the left. Zeros that are also insignificant or don't tell us about precision are zeros that are in front of a number without a decimal. So this one here, it's 85 or 850,000 meters. There's no decimal here though, so I don't know if these zeros are precise or if the person measuring it only measured it to the tens of thousands place. Were they really loosey-goosey and just saying, oh, it's 850,000, or is it like precisely 850,000? I can't actually tell you that. So I have to go with like what I know for sure. And I know for sure these two numbers are significant. So this would be 2 sig figs. Same thing with this one. Is this 1,250,000 right on the nail? Or is it, somewhere guesstimated in the tens of thousands place? I can't tell. So I can only go with what I know for sure, which is the 1, the 2, and the 5. Those are significant. So 3 sig figs. Okay, well, yeah, we'll talk about that. So what happens? So sometimes they call this ambiguous. If I have something like 6 million, okay, and it's written like this. I don't know how many significant figures the zeros pertain to. I know the 6 is significant for sure. So I would say that this has 1 sig fig. But what if you know for a fact that like these 3 zeros are significant? So the 6 is significant and you want to include these 3 zeros, not these ones, but these ones. How do you work around that? Well, the way you would do it is you would write the number in scientific notation. So if I converted this to scientific notation, I could say 6.000, include just the zeros I know are significant, 10 to the 6. And that gives a workaround for it. So here I've got 4 sig figs. That's one way to make it a little easier. If you're trying to let the reader know, oh, I don't want to include all the zeros. I just want to include some of the zeros. Head back over to those slides. So that's what they're saying here. Like, let's say if you've got this measurement of 300 meters and you know that your measurement is precise out to the tens place, you want to include that 0, you could convert it to scientific notation as 3.0 times 10 to the 2. And that would say, okay, I've got 2 sig figs. So here's some more examples of that. Zeros at the end of a large standard number without a decimal point are not significant. So if I've got this here, no decimal, really only the 4 is significant. Here, only the 8 and the 5. Remember, zeros at the beginning are just behaving as placeholders. So look at these 3 numbers. I want you to tell me how many significant figures each of those have. So first one is 0.002650. Next one is 43.026. That last one is 1,044,000. There are units on those as well, but those don't matter quite as much with the significance. So I'll give you all 2 minutes to work on that. Any place that you're indicating that a 0 is or isn't significant, maybe write a note telling yourself why, okay? So that you can remember a little bit later on why you are counting some zeros and not others. Okay. And for people in here who took Chem 092 at AV Tech, a lot of the stuff that we went over in Chem 092 is gonna be a review for probably the first, I'd say, third of the class. So if you do have your notes and stuff from that, it may be useful to pull those back out. All right, so identify number of significant figures. Oh, this also says write it in scientific notation, whatever, if you did, go for it. So this first one here, where is my main number? It starts at the 2. What are these zeros doing here in front? They're just telling you how small the number is. Like, you know, in this case, our decimal starts at the thousandths place instead of the hundredths place, but they don't give us any precision. So I can actually drop all those zeros as telling us anything about significance. The 2 is significant, the 6 is significant, the 5 is definitely significant. This 0 at the end is also going to be significant. It comes after the main number, after a decimal place. If this wasn't significant, they would have just left it off. It's giving us another dimension of precision, right? One past where the 5 is sitting. So we're gonna go with 1, 2, 3, 4 values for significant figures. B, all of those values are significant. That's a pretty easy one to see. There's a bunch of non-zero numbers, and then there's a little 0 nestled in the center. Remember, we can't have something talking about precision, lose the precision, and then go back to being precise. It's gonna come in a group or a unit. This one down here, there's some ambiguity. We know the 1 is significant. We know the 4 and the 4 are significant. And then this 0 sitting in the center is significant. These zeros, we don't know if they're significant or not. We can't, from the way it's written, we can't decide. So we're gonna say 1, 2, 3, 4, 4 significant figures here. These guys are telling us about precision. This is just telling us how big or small the number is. And you can write them in scientific notation. Okay, measured values are different than exact numbers though. So exact numbers are going to be anything that's not measured and they don't have a limited number of significant figures. So they do not affect the number of significant figures when you're running a calculation. They're numbers obtained by counting, or they come from definitions like a conversion factor. So all these are examples of exact numbers. 8 cookies. It's kind of like saying 8.000000 with the zeros running all the way to infinity, because it's like you can't get more precise than 8 cookies. 6 eggs, right? There's a discrete amount. And then these are conversion factors. So 1 quart equals 4 cups. That isn't up for debate or precision. You're not going to get better at relating those two by having like a better measuring cup. That is just the definition of what those two are. So we say they have an unlimited number of significant figures. So if you were to ever use those in a calculation, you would just run off with unlimited sig figs. We'll do some of those a little later. So that'll make some more sense. So here are some other examples of exact numbers, items, anytime you're counting them, conversion factors, or defined, sometimes they're called equalities. 2 things that are equal to each other, you would say have unlimited sig figs. So looking at these three things, it says identify these as either being measured or exact and give the number of significant figures for each one. So 3 coins, that's going to be an exact number. Sig figs, it's unlimited, right? We don't have any restriction on how precise that is. The diameter of a circle is 7.902 centimeters. That's a measured value, right? If you had a better ruler, you might actually be able to get an even more precise diameter. So we will want to include sig figs here. In this one, we've got 1, 2, 3, and 4 sig figs. And then 60 minutes in an hour, that's an exact number, right? We're not going to get more precise with that. 60 minutes is equal to an hour. That is its definition. So these significant figures are going to come into play when we're running calculations in our class, because if you have one piece of information that's really, really precise and you have another piece of information that's kind of cruddy, and you have to multiply them together, your final answer is only going to be as precise as the cruddy one. I mean, you've probably had this happen before where you've had two numbers and you've put them into a calculator and they've given you this really long trailing decimal and you're like, how many of these numbers am I supposed to use? If they're measured values, there's actually a specific amount that you want to use. So if you have a calculator or your cell phone available, you will want that for these. So when I'm taking two numbers and let's say multiplying them together, the final number needs to be rounded to the correct number of sig figs. So let's talk about the rules of rounding. If the first digit to be dropped is 4 or less, then the number will stay. If the first digit to be dropped is 5 or greater, then the last remaining digit is going to increase by 1. This is like old school rounding from, I don't know when you learn rounding, what, second grade, something like that. Who knows? I really haven't, I don't remember. But let's look at a number. So 16.4. Let's say I want to round this to 2 sig figs. Right now, how many sig figs does it currently have? It currently has 3. For calculation purposes, let's say we can only honor 2 sig figs. So how do I round 16.4 to 2 sig figs? Well, the way that I go about this, I start all the way over to the left. I'm going to keep the 1 and I'm going to keep the 6. That's going to give me the 2 sig figs. So I have to drop everything else. So I look at the 4. The 4 is going to tell the 6 to stay. So to round this to 2 sig figs would be 16. What if this number, instead of being 16.4, happened to be 16.5 sig figs? Okay. And I also want to round it to 2 sig figs. I'm going to keep the 1. I'm going to keep the 6. What does the 5 tell the 6 to do? It's going to tell it to actually round up. So 2 sig figs here is going to be 17. Right? You guys remember the rules of rounding from long, long ago? Okay, so 4 and under, it stays. 5 and over, it goes up. Let's look at some situations where we want to round and it doesn't always, it's not always as intuitive. One situation I see happen a lot, 4.449. I want to round this to 2 sig figs. I'm going to keep the 4. I'm going to keep the 4. I'm going to cut everything else off. This 4 tells this 4 to stay. So this would be 4.4. What I have had happen before is students will say, oh, well, doesn't the 9 tell the 4 to round to a 5? And then the 5 tells the 4 to round to a 5. You only use the number, the first number that's getting dropped. Everything else gets ignored. Because what if you had a number like 4.444449 and you just wanted 2 sig figs? Do I have to go through this process of hopping all the way down the line? No, we just use the 4. We ignore everything else. Another situation I see happen is, let's say we have 1,327,551. And I want to round this to 4 sig figs. So start over on the leftmost side of the main number. We'll keep the 1, we'll keep the 3, we'll keep the 2, and we'll keep the 7. So this 5 here is going to tell this 7 to roll up. So I'll have 1, 3, 2, 8. And then I'll get students stopping there. And I'll tell you right now, 1,327,551 does not round to 1,328. The magnitude in those is different, right? Where did the million go? Now we're in the thousands. So all spots that get dropped before an inferred decimal, you need to replace those with zeros to keep the magnitude of the number. So I'll give you another one. Let's say we have 8, 5, 2, 4. And I want you to round this to 1 sig fig. So 8, 5, 2, 4 rounded to 1 significant figure. Okay, hopefully from the previous one, you are rounding this to, you're not rounding it to 9, you're rounding it to 9,000, right? So we're filling the zeros in because 8,524 would round to 9,000, not 9. That would change the magnitude of the number. Sometimes you need to add significance, like in the case of that one where we had the ruler and we needed to add the decimal. So let's say I've got a value of 4, but I really needed to have 3 sig figs. Okay, let's say the calculator pooped it out and 4 was the answer, but it needs to have 3 sig figs. How do I add significance to this number? I add a decimal and then I put zeros on the end until I get to the desired amount of sig figs. So we're not going to say that the remaining answer is 4. We're actually going to say it's 4.00. It's precise out to the hundredths place. I'm trying to think if there's any other kind of wonky situations we get ourselves into with rounding. I think that covers most of it. So let's look at this guy here. We've got this number, 3.1457. Round it to 2 significant figures and then also round it to 3 significant figures. Okay, so if we want 3 sig figs, that means we're going to keep the 3, we're going to keep the 1 and the 4. The 5 will tell the 4 to go up, so we would have 3.15 for 3 sig figs. What if we only wanted 2 significant figures? I'd keep the 3 and the 1, and then the 4 would tell the 1 to stay, so it would just be 3.1. Again, the 5 doesn't tell the 4 to become a 5, that then moves down the chain. We've got 3.15 and 3.1. So now that we're good with excuse me, rounding, let's talk about when we're actually running a calculation. So multiplication and division are sort of the inverse order of operation, right? The opposite of multiplying is dividing. Opposite of dividing is multiplying. Whenever we're doing either of these operations, which encompasses like, I would say 95% of the calculations we're doing in this class, your final answer can only honor whichever number had the fewest number of significant figures or your least precise piece of information. Okay, so if we look at these two numbers here, and I take 24.66 centimeters and I multiply it by 0.35 centimeters. This number here has 4 significant figures. This number over here only has 2 significant figures. So my final answer, although the calculator displays a number with 4 sig figs, I can only honor 2 sig figs. Good piece of information, not so good piece of information. So my final answer can only be as precise as my weakest piece of information. So I would have to then round my calculator answer into a number with 2 significant figures. That happens no matter how many multipliers and divides you string together. Like if we look at this one, 21.5 times 0.30 divided by 1.88. This gives us a really long number in the calculator. This second value is our limiting value. This only has 2 sig figs where the others have 3. So my final answer can only honor that weakest piece of information or precision. So we would go with 3.4. And I know some people, this drives them a little nutty because they're like, look at how precise my calculator answer is though. It gave this to me, it's so precise. All this information you can almost think of as junk because these numbers they're measured values. They're not very precise. So this isn't, we can't create a false like illusion of precision. We can only go towards whatever the weakest is. This is that situation I was talking about where you might have to add precision. So what if we took 6.0 grams and divided by 2.00 grams? All right, well, I'm sure we all know 6 divided by 2 is 3. So it doesn't matter how many zeros are tacked on the end, the calculator is going to pop it out as 3. But these are measured values. So we need to bring that measured information with us. This has 2 significant figures. This has 3 significant figures. The final answer written like this only has 1 significant figure. I have to give it a little bit more significance or precision. The way that I do that is I hit a decimal and then I tack on a 0. And you can add as many zeros as you need to get that certain amount of precision. So let's say, this was 6.0000 and this was 2.0000. We needed like 5 sig figs. I would tack on 4 more zeros to get that precision. Does that make sense why you would add a 0? Happens when you divide 2 numbers that really fall kind of perfectly and you end up with a whole number. You got to let your reader know, well, it isn't actually a whole number. Okay, so it's going to seem really silly, but I want you to take this, I want you to do this calculation. So plug it into your calculator. You're going to get a number. And then I want you, the more important part is I want you to round it to the correct number of significant figures. So 5.00 centimeters times 3.408 centimeters divided by our 2.0 centimeters. Give you just a minute for that. Okay, so when you run this through your calculator, you should end up getting a value of 8.52 centimeters. The units are centimeters because, where did you go? one of these centimeters cancels with one of these centimeters, so you just have a unit of centimeters. But this has 3 sig figs. This has 3 sig figs. This has 4 sig figs. This has 2 sig figs. This becomes my limiting significance. So I can only use the 8 and the 5. The 2 tells the 5 to stay. So we get 8.5 centimeters, 2 sig figs. The slide, I don't know why it gives you 3 sig figs. Sometimes these slides are more work than they're worth. So that 2 should not be there. Go away. All right, 2 sig figs. So what if you're doing addition and subtraction? Addition and subtraction is going to follow a different set of rules. Just like multiplication division are the opposites in that order of operation, addition and subtraction are also opposites. In this case, whenever you're adding and subtracting numbers, your final answer will get rounded to the same number of decimal places as the measurement with the fewest number of decimal places. So you go off of decimal places as opposed to significance. So looking at these numbers here, if we take these 3 numbers and we add them together, the calculator is going to pop out 66.102. Some of this information is junk though. This number here has precision to the thousands place. This number here has precision to the hundredths place, and this one has it to the tenths. So my final answer has to be rounded to the tenths place. So we'd go with 66.1. Doesn't matter that this has 2 sig figs and our final answer has 3 sig figs. When we're doing addition subtraction, we don't worry about anything with sig figs. If we subtract 2 numbers, same rule applies. So this is got precision out to the hundredths, this has it out to the tenths. Final answer will need to be honored out to the tenths place. It does help sometimes with addition and subtraction to line them up like you would in grammar school where the decimals all match up, because then you can just sort of see what you need to cut off, right? This is the smallest guy with the decimals, but you don't have to do it that way. Okay, so try this one here. Calculate it out and then round it to the correct decimal. Okay, so when you run this through your calculator, you should get 104.409 milligrams. A lot of this is junk information though. We can only go to the tenths place. So I need to cut off the 0 and the 9. The 0 tells the 4 to stay. So 104.4. Again, it doesn't matter that this only has 3 sig figs and your final answer has 4 sig figs. We don't use the sig figs for addition and subtraction. All right, so within the metric system, what's really nice about it is a system based off of factors of 10, 100, 1,000, 100,000, a million. And we can change our units. We can make bigger units or smaller units by taking out like what we would call a base unit, like a meter, and adding a prefix like kilometer or centimeter. That's what's so nice about these prefixes. So a prefix is a special feature of just the SI system and also the metric system, where we can place something in front of the base unit to increase it or decrease it by some sort of factor of 10. This is not the case with the British system. We don't have, like a foot isn't our base unit. And then if we want to make a bigger unit, we have a kilofoot. Or if we want to make a smaller unit, we have a centifoot, right? We actually have to change the name. We have a mile, we have an inch. But in something like gram, for instance, if I want to make, let's say, a smaller unit, I can add something like a milli, and we have a milligram, which is smaller than a gram, specifically by it's a thousandth. We can even go tinier than that. We could do a microgram. So here are some of the prefixes. These are prefixes that will increase the size of a unit. So we've got kilo, which is 1,000 times bigger. We have mega, giga, and then you may have heard of a gigabyte, a terabyte. Those are all talking about larger factors. These are how much bigger they are. What are examples of base units? A meter. So a base unit could be a meter. It could be a liter. It could be a gram. It could be a second, a joule, which is a type of energy. There's a couple more, but these are, you always have one of these and then you'll insert one of these in front of it. So I could make it a kilometer, or I could make it a megaliter, right? Or I could make it a teragram by adding these different prefixes to the front. These are prefixes that make it smaller. So a deci, like a deciliter, is a tenth of the base unit. A centi, like a centimeter, is 100. A milli is not a million, it's 1,000. Then we have a micro, which is a millionth, a nano, and a pico. So traditionally, right, you'd kind of have to have these memorized. But because we have open book, you don't have to have them memorized, but definitely have them accessible and feel comfortable with how to reference them and how to use them. The ones that sit pretty close to the base unit, I have a little trick to remember them. King Henry died before drinking chocolate, milk. Okay, the B, the before, this is your base unit. So this is base. So this could be, again, a meter, a liter, a gram, a second, a joule, a bunch of different things. Each of the letters are hops of a factor of 10. So if we, moving to the left, these are bigger units, and to the right, these are smaller units. So we've got a deca, we've got a hecta, or hecto, we've got a kilo. We don't use these two so much, but we definitely use kilo. Here I've got my deci, my centi, and then my milli. And I just find this helpful when I'm wanting to convert between units, because let's say I'm given, and we're going to do a bunch of conversion factors, but I'm just going to show you this real quick. Let's say we're given that we have 182 meters, and I want to find this in a unit of kilometer. The way that I do this is, well, meter is what type of unit on here? Does it have a prefix? No, it's prefixless. So we're starting at the before, or the base. I want to go to kilometer. So where is kilometer? Kilometer is king all the way over here. So how am I going to get from the base unit to the king? I have to take 3 hops to the left. 1, 2, 3 hops to the left, which means I move my decimal 3 places to the left. So where is my decimal in this number? It sits right there. If I'm moving it 3 to the left, 1, 2, 3, 0.182 kilometers. You've got it done. That's the beauty of the metric system, is you just move the decimal to get different units, as opposed to the British, where it's like, if we want to go from miles into inches, you've got to divide by 5,278, you got to divide by 12. It's a total pain. So let me give you one. Let's say you're given that you have 8.2 kilometers. I want you to find how many centimeters this is. Okay, so hopefully that didn't take too long. In this instance, I'll use a different color. We're starting at kilometer or king, and I want to get to centimeter, which is our chocolate over here. So I've got a hop. 1, 2, you do go through your base, 3, 4, 5. So the decimal needs to move in that same direction, 5 hops. So my 8.2, well, that's going to go 1, 2, 3, 4, 5. I'm going to fill in those empty spots with zeros and add my units. So it becomes, let me clean it up here, 8, 2, 4 zeros, comma here. So 820,000 centimeters. So that's kind of a quick way to at least hop around the units that are closest to the base. Are there ones outside of this? Yes, like if we go over here to kilo, we can see kilos here. All right, then if I hop by 3 more zeros, I get to mega, 3 more zeros get to giga and tera. So you'd have to take quite a few hops to get up to tera. Same thing here, we only covered it to milli, then you can get smaller, right? Micro, nano, pico. But that one might be helpful just to get you through some of the more usable conversions. So this is one thing to note too. The relationship of a prefix to a unit can be expressed by replacing the prefix with its numerical value. So for example, if I have a kilometer or a kilometer, kilo has the same value as 1,000. So kilo can just directly get replaced with 1,000. So a kilometer is equal to 1,000 meters. What about a kiloliter? The kilo again is representing 1,000, so it would be 1,000 liters. Instead of saying something like kilo, let's do something a little bit bigger. If we were to say like a teraliter, I would say a teraliter would be equivalent to 10 to the 12 liters. All right, you use that number in replace as a replace of the actual prefix. So prefixes, yeah, there's, if you've ever looked at daily nutrient values, like on the back of some food, or it looks like this is what we need to be eating throughout the day, they use prefixes. So we can see here for protein, we need 44 grams. Vitamin C, we need 60 milligrams. A milligram is 1,000th of a gram, so much less vitamin C than we do need protein. Vitamin B12, right, we need 6. This is a microgram. This is even tinier than our milligram. So those are what those numbers are sitting in front of the gram value. All right, so fill in the blanks with the correct prefix. Okay, so go ahead and try this. So what is equivalent to 1,000? This is what is equivalent to 1,000th, and this is 100th. I'll give you just a minute for that. I just gave you all the answers. Give it a try. Okay, so for this first one, 1,000 meters. Well, what is 1,000? That's the same thing as a kilo, so a kilometer. People get very, very freaked out by scientific notation. Don't get scared. If you want, you can even move the decimal out to show it in a decimal form. But the prefix for 1 times 10 to the negative 3, which is 1,000th, is the same thing as a milli. So 1 times 10 to the negative 3 grams is the same thing as 1 milligram. And then this is 100th, right? If we move the decimal over, it's a 10th place and then 100th place. 100th of a meter is the same thing as a centimeter. So are you guys liking the metric system? It's kind of cool. It's a little bit more useful than, super sexy. It's a little more useful than like our British system, which we can't convert so conveniently. Couple, I'm going to show us a couple different units here. Yes, Miley's into it. She's into the metric system. All right, so measuring length, we're going to use meter. 1 meter is the same as 10 decimeters, right? These bigger tick marks are the tens. Cut it up into 10 slices. It's also equivalent to 100 centimeters. So the smaller ticks, I could cut those up 100 or 1,000 millimeters. So the little teeny tiny ticks, if we were to zoom in on there should be 1,000 of those within each meter stick. If I was to take this meter stick and line 10 of those meter sticks up, I would get a decameter. If I was to line 100, I'd get a hectometer. If I was to line up 1,000 meter sticks, I would get a kilometer. Measuring volume, so volume in liters. A lot of times we see the unit for deciliters. And so if we were to take a liter and divide it into 10 equal parts, we would get a deciliter, right? This, just because we're changing the base, the relationships stay the same. 1 liter is equal to 1,000 milliliters. 1 liter is equal to 10 deciliters. So that doesn't change. For volume, sometimes we use this thing called a cubic centimeter. And I know a lot of you guys are going into some sort of medical field, whether it's vet tech or nursing or nurse's assistant or something like that. And you will be using something called a cc, right? When you're administering medication. A cc is equivalent to a cubic centimeter. Now, a couple nifty things here. A cubic centimeter, which is if you think of a little box that's a centimeter by a centimeter by a centimeter, is the same volume as 1 milliliter. Okay, so that's a nifty conversion. 1 milliliter is the same thing as a cubic centimeter. Yes, every day. Yeah. So you'll see some of you may be a little bit more familiar with the CC. Here is an image of, we've got our little cubic centimeter. This is a decimeter, right? So a decimeter would be 10 centimeters, a decimeter would be 10 centimeters. So 10 by 10 by 10. If we wanted to look at just one little centimeter cube, we'd pull just one of those little cubes out. We could put it in a vial. Measuring mass. So when you visit the doctor for a physical exam, he or she records your mass in kilograms and your laboratory results in micrograms. Here are some relationships. So we've got, okay, I've never been to the doctor and they've never given me my weight in a kilogram. If they did, I'd be very happy because it would be a much lower number than it is in pounds. Usually I get it in pounds. If we were in other places, they give it in kilograms. But again, the prefixes mean the same thing even if we change the base unit. So 1 kilogram is equal to 1,000 grams. I feel like this, we're sort of beating a dead horse at this point. This is useful. So identify which unit is larger. So a millimeter or a centimeter. Which one do we think is larger? The centimeter, right? That's 100th versus 1,000. Which is larger, a kilogram or a centigram? Oh, definitely a kilogram. A kilogram is moving on the bigger side of our base. Centi is smaller. A milliliter, or this like funky U, is known as a microliter. The milliliter is going to be bigger. And then kiloliter versus, do you see this MC here? That's another way of saying microliter. Okay, so this and this are the same unit. Definitely the kiloliter is going to be bigger. Okay, so we are going to stop there for lecture for right now. Let's just, for this first week, let's take a quick look at the syllabus together. Just for, I mean, literally we'll do it for a minute. So that we're on the same page about due dates. So you have a couple things that are going to be due for you on Monday, or Sunday rather. So I want you to, I don't want you to miss those. Go down to the bottom part here. Week 1, we've finished chapter 1 and we actually started getting into chapter 2, which is great. You need to get that syllabus verification done. So look through it, go on Moodle and verify the syllabus. And then you have your first Mastering Chemistry assignment, the chapter 1, which we only went over a little bit of. So go ahead and get started on that. For next week, chapter 2, we've already got a head start on this chapter 2. So hopefully next week, maybe we can even finish lecture a little early one of those days. So for you guys, get your verification and get your first Mastering Chemistry homework done. Okay, so Astrid, I'll check in with you in just a second on that, okay? So yeah, we're good to go. You guys are good to go. If you have any individual questions, feel free to stay around and we can talk about it. Otherwise, have a good weekend. Hopefully I'll be in better shape next week. I'm already feeling better, but not quite 100% yet. But it's nice. It's been nice meeting y'all, and yeah, I'll see you next week.